All right, let's look at composition analysis, determining formulas. So in the warm-up, we have, we're talking about forensic investigations where they collect samples from crime scenes. And how do technicians identify unknown samples? Well, we have an instrument known as a mass spectrometer that can identify compounds because each compound has a unique mass spectrum, kind of like you have a unique fingerprint. And it breaks most of the molecules into fragments, and then we can see them as marks along this axis. It marks the mass of each of the particles, and the height of the line tells you how much of it is present in that sample, so what its abundance is. And this is a simplified mass spectrum of a compound known as pentane. And we're going to take a look at some questions. It says the last spectral line represents the intact molecule. What is the molecular mass? So this is the last spectral line right down here. What is its molecular mass? I would say it's around 72 atomic mass units. Number 2 says draw an arrow to point to the spectral line that represents the mass of the outlined fragment. So this outlined fragment here is 2 carbons and 5 hydrogens. So it's C2H5. So that means its mass would be 2 times 12.01 for your carbon plus 5.05 for hydrogen because they're 5 at 1.01 each. So that means that this is going to be around 2830-ish. So 29.07 to be exact, I believe. So we're looking somewhere over here for the spectral line that represents that mass. Why do you think there are more of some fragments than others? Well, it's easier to break weaker things. So one would argue that weaker bonds are broken to create a fragment. And the important point here is that one of the most sophisticated tools in a chemist's arsenal identifies compounds solely from their mass profile. So in this section, you're going to learn how to determine a compound's formula from its composition by mass. So let's talk about percent composition. Percent composition is the percent of a compound's mass that is contributed by each type of atom in the compound. And percent composition is, you can think of it as part over whole times 100. So what do I mean by that? I have 12 carbons, 22 hydrogens, and 11 oxygens in C12H22O11. So if I take the mass of 12 carbon, that would be 12 times 12.01, and I divide it by the mass of the entire compound. And I multiply that by 100. That will give me the percent of carbon. So I have 144 grams of carbon. This came from 12 times 12.01 from the periodic table. The mass of the compound is 342. Multiply that by 100, I get 42% carbon. For the percent hydrogen, I have 22 hydrogens. 22 times 1.01 gives me the mass of hydrogen in the compound divided by 342 times 100. You have 6.4% hydrogen. For the oxygen, we have 11 of them. 11 times 16 is 176. Divided by 342 times 100, I get 51.5% oxygen. Ideally, these percentages should add up to 100 for a sample. Sometimes they will add up to 101. Sometimes they may be 99. It just depends. Let's take a look here at the practice problems. Ibuprofen, a common pain reliever, is anti-inflammatory. Its formula is C13H18O2. What is the percent composition? Well, I have 13 carbons at 12.01, so this is the mass of carbon in the compound. I'm going to divide that by the mass of the entire compound. So the mass of that entire compound is going to be 13 times 12.01 plus 18 times 1.01 plus 2 times 16. And then we multiply this by 100, and you're going to get 75.68% carbon. Okay? For our hydrogen, we have 18 hydrogen times 1.01 divided by the mass of that compound, which is 206.31. That's what you get when you add all of that together. Times 100, you're going to get 8.81% hydrogen. For the oxygen, we have 2 of them, so it's 2 times 16 divided by 206.31 times 100, you're going to get 15.51% oxygen. Now, if you only have 2 compounds, or 2 elements, excuse me, in your compound, if you find out the first percentage, you can just subtract that from 100 to get the next one. If you have 3, find out the percentages of 2 of them, and then you could subtract those percentages from 100 to get the third, if you want to. For number 2, ammonium sulfate is a common fertilizer used to lower the pH in soil. Calculate its percent composition. So we've got 2 nitrogen, and we're going to divide that by the mass of the entire compound, which is 132.17. That's from 2 nitrogens, 8 hydrogens, 1 sulfur, and 4 oxygen added together. That's going to give me 21.20% nitrogen. And then for my hydrogen, I have 8 hydrogen. Divided by the mass of the compound, you're going to get 6.11% hydrogen. And then for sulfur, I have 1 sulfur, so that's going to be 32.07 divided by 132.17 times 100. So this is 24.26% sulfur. If you wanted to subtract these percentages from 100, that's how you could get your oxygen. Otherwise, it's 4 times 16. And that's going to give you 48.42% oxygen. Okay? Now, for number 3, it says many salts are hydrated, which means they have water molecules incorporated into their crystal lattice in a fixed ratio. Magnesium sulfate heptahydrate has 7 water molecules incorporated. Calculate the percent of water by mass in magnesium sulfate heptahydrate. So we have 7 waters, so 7 times the mass of water, which is 18.02 grams. So this is the mass of water. 18.02 came from 2 times 1.01 for your hydrogen and 16 for your oxygen. So this together gave you that 18.02. You're going to divide this by the mass of the compound, which is 246.52. And then you'll multiply it by 100. Now, I want to make sure that you don't mess up getting the mass of the magnesium sulfate heptahydrate. Magnesium is 24.31. Sulfur is 32.07. You have 4 oxygens at 16, plus your mass of your 7 waters. Make sure you are adding the mass of 7 waters and not multiplying the mass of 7 waters by the mass of magnesium sulfate. So this is plus 7 times 18.02 for your water. This is going to be 51.17% water. Okay, now let's talk about empirical, molecular, and structural formulas. Every molecular compound, which is a compound made of nonmetals, has three formulas. The empirical formula, which is the simplest ratio of atoms, so that means if you can't simplify the subscripts anymore, you have the empirical formula. The molecular formula, which is the actual number of each atom. And the molecular formula is often a multiple of the empirical formula. Sometimes it's the same. And then you have the structural formula, which shows how the atoms in the molecule are arranged. So let's take a look here at this quick check. If I have a structural formula that looks like this, my molecular formula would be C2, because I have 2 carbons, and then I have 4 hydrogens, and then I have 2 oxygens. The empirical formula of that molecular formula would be the simplest ratio of my atoms. So that means I would divide each one of these subscripts by the same number, which is 2. And when I divide that by 2, I'm going to get CH2O. My structural formula here has 2 carbons. I have 2 hydrogens. And I have 4 oxygen. So since all of these subscripts are divisible by 2, I would simplify it to CHO2. Now, we can determine the empirical formula from percent composition. So if you have the percent of each element in a compound, you can drop the percent sign and convert them to grams, or just write grams in the percent's place, convert them to moles, divide by the smallest mole, and you'll have your empirical formula. In this sample problem, you have the percent carbon, hydrogen, and oxygen. Drop the percent sign in each. This would be 48.65 grams of carbon, 8.11 grams of hydrogen, 43.24 grams of oxygen. Divide by the molar mass of each to get moles. The smallest mole is 2.7025. Divide each by that smallest mole. That will give you these ratios, 1.53 and 1. If you are within 0.1 of a whole number here, you can stop, but you weren't because of this 1.5. If you end up with a 0.5, multiply everything by 2. So that will give you this C3H6O2, which is your empirical formula. Now, I'm going to be going over these steps over and over again to where you finally pick them up. So let's take a look at some practice problems. I have a percent of lithium, carbon, and oxygen. We want the empirical formula. I'm going to replace the percent sign with a G for grams. First step, convert grams to moles. So that means we're going to divide, and for space sake, I'm going to set this up a little bit differently. The molar mass for lithium is 6.94 grams per mole. Grams will still cancel, giving me my moles of lithium. When you are doing empirical formula calculations, write your moles out like 4 or 5 places past the decimal. Don't round them to the proper number of sig figs. Carbon is 12.01. Oxygen is 16. Now what you're going to do is you're going to divide each mole by the smallest mole that we have, which is this 1.3572. 1.9 is within 0.1 of a whole number. So that means you can go ahead and make this 2. I'm going to divide oxygen by 1.3572. That's going to give me 3.0. My empirical formula is Li2. The 2 comes from here. And C, I have 1 of them. And then I have 3 oxygens. So Li2CO3 is the empirical formula. Number 2, I have percent carbon, chlorine, and fluorine. We want the empirical formula. So you convert your grams of carbon to moles of carbon. Remember, do not round off the moles. Take it 4 or 5 places past the decimal. And then we have 58.6 grams of chlorine. Its molar mass is 35.45. And then 31.4 grams of fluorine. We're going to divide that by 19. Once you get your moles, you're going to divide by the smallest mole. So the smallest mole present would be the moles of carbon. So divide that by itself to give you 1. Divide chlorine by the 0.8268 to give you 1.9. Note that this is within 0.1 of a whole number. That means you can round it to 2. And then divide your moles of fluorine by the 0.8268, and you're going to get 1.9, also within 0.1 of a whole number. So you may round this up to 2. And your empirical formula is C. You have 1 C, you have 2 chlorine, and you have 2 fluorine. So CCl2F2 is your empirical formula. Now, in number 3, they gave you the mass of silver, sulfur, and oxygen in a compound. So you know that you need to convert each one of these masses to moles by dividing by their molar mass. Take your moles 4 or 5 places past the decimal and do not round. Then you're going to divide by the smallest mole, which is going to be this 0.02656. You're going to get 1.9 over here on the silver, which means you can round that to 2 because it's within 0.1 of a whole number. And then when you divide the oxygen by 0.02656, that's going to give you a 3.9, also within 0.1 of a whole number, so you can round that to 4. So you're going to end up with Ag2S1 and then 4 oxygen. So Ag2SO4 is the empirical formula. Okay, let's talk about determining the molecular formula of a compound. The molecular formula's mass is just another way of saying the compound's molar mass. And so when we're looking at a molecular formula, it is likely going to be a multiple of the empirical formula, which means the molar mass of the empirical formula can be multiplied by a whole number to give me the molar mass of the molecular formula. So the empirical formula can also be multiplied by a whole number to get me to my molecular formula. So let me show you what this looks like. If I am looking here at this sample problem, they gave me an empirical formula of CH2, and they told me the compound's molar mass is 42 grams per mole. Find the molecular formula. Well, if I have the empirical formula and its mass is 12.01 for carbon plus 2 times 1.01 for hydrogen, which is around 14. If I take the mass of the molecular formula and I divide it by the mass of the empirical formula, so this is going to be the molecular formula mass divided by the empirical formula mass, you will get a whole number. Because the molecular formula should be a multiple of the empirical formula. So if I divide their masses, it should give me a whole number, and that whole number is what I need to multiply the empirical formula by to give me my molecular formula. Okay? So if I'm looking at the practice problems on the next page, the molar mass of acetic acid is 60 grams per mole. Its empirical formula is CH2O. What's the molecular formula? So if the empirical formula, which is the simplest formula, is CH2O, and I'm trying to find the molecular formula, which is a multiple of the empirical formula. That means this times some whole number should give me the molecular formula. This molar mass is the mass of my molecular formula. I use the periodic table to get the empirical formula mass, which is 12.01 for carbon, 2 times 1.01 for hydrogen, and 16 times oxygen. So when I add these together, this is going to be 30.03 for the mass of my empirical formula. 30 times what whole number is 60? Well, 30 times 2 is 60. So that means CH2O times 2 will be my molecular formula, which is C2H4O2. Let's take a look at number 2. A compound has an empirical formula of C3H4. Which of the following are possible molar masses of the compound? The mass of this is 3 times 12.01 for carbon plus 4 times 1.01 for hydrogen. So that means that this is 40.07 grams per mole. So the molar masses of the molecular formula must be either the same or a multiple. There's no way it's 20. There's no way it's 55. Could it be 80? Sure, because 40 times 2 would be 80. That's a possibility. Could it be 120? Sure, 40 times 3 is 120. All right, let's look at number 3. A small sample of antifreeze was analyzed. It contained 45.1 grams of carbon, 1.13 grams of hydrogen, and 6.01 grams of oxygen. From the elevation of water's boiling point, it was determined that the antifreeze's molar mass was 62 grams per mole. What is the molecular formula of antifreeze? We need to convert, they didn't give us the empirical formula, so we have to convert all of these to moles so that we can get the empirical formula and figure out the molecular formula. So I'm converting each one to moles by dividing by their molar masses. And then I'm dividing by the smallest mole, which is 0.3755. I'm going to get 1, 2.9, and 1. 2.9 is within 0.1 of a whole number, so I can round that to 3. My empirical formula is CH3O. Now, to figure out my molecular formula that has a mass of 62, I need to figure out the mass of this empirical formula, which is 12.01 for carbon, 3.03 for hydrogen, and 16 for oxygen. So this is 31. 31 times 2 is 62. So CH3O times 2 is C2H6O2, which is my molecular formula.